Okay, here is the second part of 1.7, continuing with our word problems. This problem involves a small satellite dish, and it is packaged with a cardboard cylinder for protection. It says the parabolic dish is 24 inches in diameter and 6 inches deep, and the diameter of the cardboard cylinder is 12 inches. They want to know how tall must the cylinder be to fit in the middle of the dish and be flush with the top of the dish. So what we're doing essentially is we have this satellite dish, okay, and you guys have seen satellite dishes before. It takes the form of a parabola. Well, first of all, it says it's parabolic, okay. Now it says the diameter is 24 for the dish. Okay. Now, here's the cardboard. Okay. Alright. It's 24 inches across and 6 inches deep. Okay. So they want to know how tall is this cylinder. Okay. How tall is that cylinder to fit so that it fits in the middle of the dish, so it's in the middle, and it's flush with the top of the dish. What that means is that the top of this cylinder goes right up against there. Okay? Now, here's the thing. If I were to think about this in terms of points, coordinates, okay? That's about halfway across. I mean, if I was thinking about a coordinate plane, and these points right here, okay, if this is halfway, we could call that like 0, 0, which would make this 12. Actually, this would be 0, 0 down here. Not this. Okay. Alright. Which would make that point 12, 6, because remember, this is in the middle of the 24. Now, if I went the other way, I would be at negative 12, 6. Okay. Because from 0, 0, I go to the right 12, up 6. Right, or left 12, up 6. Okay. Now, what happens when the parabola is wider? That is a vertical shrink, not a stretch. Remember, the stretch makes the parabola thinner. Now the parabola is wider. So now the question is, here's my equation. What's K? What number makes that shrink? Well, the reason I found these points, okay, alright, the reason I found those points is because now I can plug one or both in for X and Y, okay, because I want to find out what K is. So 6 is K times 144, divide by 144. So K is 6 over 144, which reduces to 1/24. Now here's what that means. That means that the equation for my parabola is 1/24 x squared. Okay? Now, that would make sense if you think about it, because the parabola is wider. That means that your number in front of x is going to be very small, 1/24. Okay? So that's how we know that it's a little bit wider, or wider, we have the smaller fraction. Okay? Now, we need to find the y-coordinate of the parabola that's 6 inches from the center. Okay? So in other words, when x equals 6, what is the y-coordinate? So what is this point here? Okay. So, y equals 1/24 times 6 squared. Okay? So 6 squared is 36. 36 over 24. Sorry guys, I'm running out of room. Running out of room here, guys. I apologize. So this is 1.5. So this point right here is 6, 1.5. So this is at 6, this is at 1.5. So if I want to find out how tall the box is, or the cylinder is, do 6 minus 1.5. It's 4.5 inches. Okay? So, just to recap, we had to figure out what the equation of the parabola was. To do that, we plug in one of the points. And by the way, when I plug in negative 12 for x, negative 12 squared is still 144. So it doesn't matter which of the 2 points you plug in. Okay? The parabola itself, the dish itself, is 6 inches tall. We had to find this point right here, to be able to figure out the difference between the top and the bottom. So that's how we got 4.5 inches. Okay. Next example. Grain is leaking through a hole in a storage bin at a constant rate of 8 cubic inches per minute. The grain forms a cone-shaped pile on the ground below. As it grows, the height of the cone always remains equal to its radius. If the cone is 1 foot tall, how tall will it be in 1 hour? Okay. Now, first thing we have to do is figure out volume of a cone. So the volume of a cone is 1/3 times pi r squared h. Okay. Now, the height and the radius are always equal. All right. So we can get volume directly as a function of the height. So, if the cone is 1 foot tall, oh wait, I used the wrong. No, I'm okay. That's not the volume. Okay. Here's the deal. The radius and the height are always the same. So 1/3 pi times radius, right? Actually, that's not true. It should be the other way around. Boy, I'm really following this up. So the radius equals the height all the time. That's what it says in the problem. So what I'm going to do, h squared times h. I'm going to plug h in for r since they equal each other. So this is 1/3 pi times h to the third. That's the volume. Okay? Now, if the cone is 1 foot tall, now you don't want to put a 1 in for h because this is the rate. The rate is in cubic inches. So we want to make sure that the height is in inches. So 1 foot equals 12 inches. So 1/3 pi times 12 to the third. Okay? And that turns out to be 576 pi inches cubed. Okay? Now, that is the volume right now, because the cone is 1 foot tall right now. Now, it says 1 hour from now, what will it be? Okay? Well, it says here that the grain is leaking at 8 cubic inches per minute. Well, there are 60 minutes in an hour. So 8 times 60, that means 480 inches cubed are coming out per hour. Okay? Now, the total volume, TV, total volume, will be 576 pi, which is what it was to start, plus you got to add 480 because now it's an hour later. Okay? Now, they want to know how tall will it be in an hour. Well, now I'm going to take I'm going to skip forward a couple slides, guys. I'm going to take 1/3 pi h to the third, and I'm going to set it equal to, 576 pi plus 480. Because this is the volume of the cone after 1 hour. I want to know what the height of that cone is in an hour. So, what do? Okay, multiply both sides by 3. Whoops. So I get the 1/3 and the 3 cancel out. So pi h to the third equals 3 times 576 pi plus 480. Okay, I would not distribute the 3 in this situation, but that's just me. Okay, I would divide both sides by pi. So h to the third equals 3 times 576 pi plus 480, all divided by pi. Now you're going to take the cube root of that. So you're going to take the cube root of that whole fraction. Okay? When you plug that in your calculator, and I would absolutely do it, to practice, the height is 12.98 inches. Okay? So if we go back, all right, the radius equaled the height. So we take the volume for a cone, and we make it a function of the height. We can substitute h in for r. Here's our new volume formula. We want to find the volume of the cone right now. So we plug in, it says the cone is 1 foot tall. We take 12 inches instead of 1 foot. We figure that out, we get 576 pi. So it's 576 pi now. In an hour, we're adding 480 inches cubed. Why? Because the rate is 8 cubic inches per minute. 60 minutes in an hour times 8 is 480. So this is the total volume after 1 hour. Well, the question says, how tall will it be in 1 hour? So we have to find the height. To do that, we take the volume formula that we found, set it equal to the height in set it equal to the volume in 1 hour, and solve. Okay. How many rotations does a 15-inch radius tire make per second on a sport utility vehicle traveling 70 miles per hour? Holy moly. Per second. Well, let's break this down for just a second. Let's just break this down. So I have 70 miles in 1 hour. We're going to do a bunch of conversion factors here. Times. Well, how many minutes are in an hour? So I have 1 hour. 60 seconds in it, or excuse me, 60 minutes. Duh. There's not 60 seconds in an hour, kids. Okay. All right. All right. But how many seconds are in a minute? 60. Okay. So here's what's happening. All right. The hours cancel out. All right. Now, that's as far as I can go with that. Okay, that's as far as I can go with that. Now I do the time, or I do the distance, excuse me, do the distance. So miles, how many feet are in a mile? 5,280 feet. Okay. All right. 15-inch radius. How many inches are in a foot? 12 inches in a foot. 1 foot. Times. Okay. 1 rotation. Well, now here's the thing, guys. 1 rotation. Well, one rotation is really the circumference. Circumference 2 pi r. Well, the radius is 15. So that's 30 pi. So 30 pi goes down here. Inches. So I got a bunch of fractions. Okay, I got a bunch of fractions. Now, if we don't, let's just say for the sake of argument, we don't cancel the hours. We just leave them there. So 1 hour, 1 hour. Multiply across the top. 70 times 5280 times 12. Now you say, well, what about the ones? Well, guys, when I multiply by 1, I just get the same thing. So the ones are irrelevant. We're looking for non-1 numbers. So 60 times 60 times 30 pi. Okay? All right. So if I do that, I get roughly 13.07 rotations per second. Okay. That's pretty good. All right, so we have to use conversion factors there. Miles per hour, hours and minutes, minutes and seconds, feet and miles, inches and feet, rotations and inches. Okay. Last one. Table below records the low and high daily temperatures observed on 9/9/1999 in 20 major American cities. Of course, Cleveland's not on there. I don't know why not. We are a major American city. Find a function that approximates the high temperature y as a function of the low temperature x. Use this function to predict the high temperature that day for Madison, Wisconsin, given that the low was 46. This is easy. Okay? This is easy. The low is x, the high is y. First thing you want to do a scatter plot. Okay? Do a scatter plot. You will see that the points, when these points are plotted, okay, you're going to find that they go upwards and they go up in a line. It's sort of a linear issue, kind of a linear graph. Okay? Now, we could fit the line by sight. Now, if I fit the line by sight, that basically means I pick a point near the end and a point near the beginning, and I use slope formula and do all that stuff. Or use what we always use, lin-reg. Okay? Use lin-reg. Okay? Now, when you do that, you do the scatter plot, you do lin-reg, you're going to get this equation roughly. 0.97x plus 23. So now when it asks what is the high temperature that day for Madison, Wisconsin, given that the low is 46, well, plug 46 in for x because the lows are the x. Plus 23. Boy, I can't write. Holy cow, can I not write? 23. So, the high temperature that day for Madison, Wisconsin was about 67.62 degrees. And if you do a little research, you'll find out that the actual high temperature that day in Madison, Wisconsin, was 67 degrees. Kind of interesting. So, that's all we got. 1.7. If you need further explanation, let me know. Sorry it's so lengthy, but I wanted to make sure everybody got it the first time around. Okay?